Hey, if you're an embedded developer and you've ever felt like you're just scratching the surface with STM32, you are in exactly the right place. Today, we're going to pull back the curtain on the STM32 architecture. The goal here is pretty simple, to give you the confidence to go beyond just using those high-level libraries and start writing your own powerful, efficient, peripheral-level code. Okay, let's dive in.
Look, we've all been there. It's incredibly easy to get started with STM32 by just copying some code and letting libraries like HAL do all the heavy lifting. But to really, truly unlock its power, to debug those really tough problems, and to build professional-grade products, you have to understand the hardware that's running your code. This whole explainer is about making that leap from simply using the chip to truly understanding it.
So, what even is an STM32? Well, it's this massive family of microcontrollers, and chances are you've used the device powered by one today without even knowing it. I'm talking about everything from the smart thermostat on your wall, the fitness tracker on your wrist, to really complex systems inside cars and industrial machinery. These little chips are everywhere. They are the tiny, powerful brains that make our modern world tick.
So what's the big deal? Why are these things so popular? Well, for starters, they're all built around the incredible industry-standard 32-bit ARM Cortex-M core. That's a huge deal. They also come absolutely packed with a ton of built-in hardware blocks, we call them peripherals, for things like timing, communication, and reading sensors. Plus, they're designed to be super low power, which is a must-have for anything that runs on a battery. And maybe best of all, there's a massive ecosystem of tools that just makes your life as a developer so much easier.
All right, let's start our tour. I want you to think of the microcontroller as a tiny, self-contained city. Right at the absolute center of this city, you have the CPU, the central processing unit. This is our city hall. It's where all the big decisions are made and where all the instructions are carried out.
Now, inside our city hall, the CPU has a small set of super-fast memory locations called registers. Think of these as the mayor's personal notepad for doing quick calculations. And while the general-purpose registers are important for math, the one we really care about right now is R15, the program counter. This is the key. This one register tells the CPU what to do next, driving the entire flow of your program. The program counter is, quite literally, the CPU's GPS. It always holds the memory address of the very next instruction it needs to grab from memory and execute. So as your code is running, the program counter just ticks forward, stepping through your program's instructions one by one, telling the CPU exactly where to go next. It really is the fundamental heartbeat of your application.
Okay, so if the program counter is the GPS, what's the map it's using? Well, that will be the memory map. Every single component inside our microcontroller city, the code you wrote, your variables, every single hardware peripheral, has a specific, unique address. The memory map is the official city plan that tells the CPU where to find absolutely everything.
And here's the really great thing. ARM standardized this map across all Cortex-M devices. So if you look at the table, you've got a region for your program code in Flash, a region for your variables in SRAM, and then you see this huge chunk of memory addresses dedicated to your peripherals. This is the aha moment, right here. It means to talk to a peripheral, to configure a timer, or send some data. You're just writing to a specific memory address. It's really that simple.
Now, a city plan is great, but it's pretty useless without roads for transportation and a power grid to keep the lights on, right? Well, in our microcontroller city, data travels on roads called buses, and everything is powered by signals we call clocks. Without these two things, nothing moves and nothing works.
So let's think about this for a second. Our CPU, City Hall, wants to send a command out to a peripheral, let's say the city's port authority, which is located at a specific address on our map. How does that information actually travel from point A to point B?
It travels on something called the AHB bus matrix. You can basically think of this as a multi-lane superhighway running inside the chip. It connects masters, like the CPU, to slaves, like the peripherals and memory. And because it's a matrix, a grid of connections, it can handle multiple conversations at once. This is huge, because it means the CPU can be fetching the next instruction from Flash, while another component is simultaneously moving sensor data into RAM, all without them getting in each other's way. Okay, listen up, because this right here is the single biggest mistake that almost every beginner makes. To save power, every single peripheral in our city starts out with the power turned off. The power utility for the entire chip is a special unit called the RCC, or Reset and Clock Control. If you want to use a peripheral, you must first go to the RCC and turn on its clock. If you forget this one step, your peripheral is a brick. It will do absolutely nothing.
All right, enough theory. Let's make this real. We'll start with the most fundamental peripheral there is, the GPIO, or General Purpose Input/Output. This is how our chip actually talks to the outside world, by setting physical pins to a high or low voltage.
So let's say we want to blink a simple LED. It's a three-step process that uses everything we just talked about. Step 1, you guessed it. We go to the RCC and enable the clock for the GPIO port that the LED is connected to. We got to turn the lights on first. Step 2, we write to that port's mode register to configure our specific pin as an output. And finally, step 3, we write to another register to actually set the pin high or low, turning our LED on or off. See? It all connects.
And here's a pro tip for you. There are two main ways to change a pin's state. The easy way uses the Output Data Register, or ODR. But this is a read, modify, write operation, which can be risky. Imagine you read the register, then an interrupt fires and changes another pin, and then you write your old value back, accidentally undoing what the interrupt just did. A much safer way is to use the BSRR, the bit set/reset register. This is an atomic operation, which means setting or clearing a bit happens in a single, uninterruptible hardware step. It's a huge deal because it means you never have to worry about an interrupt messing things up. So far, our CPU has been totally in charge, just methodically stepping through our code. But what if an urgent, unexpected event happens, like somebody pressing a button? How does the chip respond immediately? That's where interrupts come in. They are the nervous system of our microcontroller city.
The hardware that manages all these events is the NVIC, the Nested Vectored Interrupt Controller. You can think of it as the city's 911 emergency dispatch center. It's constantly monitoring for signals from all the peripherals. When an event occurs, the NVIC tells the CPU to immediately stop what it's doing, save its work, and jump to a special function to handle that specific event, all with incredibly low delay.
And here's where the NVIC really shines. It can prioritize. Let's say a critical motor failure interrupt fires while the CPU is already handling a low-priority task like blink an LED. The NVIC knows which one is more important. It will actually pause the LED task, tell the CPU to handle the critical motor failure immediately, and then, once that's done, resume the LED task right where it left off. This is called preemption, and it's the magic that makes robust, real-time systems possible. So there you have it. We've toured the CPU core, we've navigated the memory map, we've traveled the data highways, and we've seen how to talk to the world and respond to events in real time. You now have the foundational map to navigate any STM32 microcontroller. You understand that it's all about enabling clocks, finding the right address, and writing the right value. The only question left is, now that you understand the machine, what are you going to build with it?
If you like this one, the YouTube algorithm says you're going to love my other videos, so go check them out.